Assalamualaikum and hi. So today we are going to present our BEL 2612 Engineering Laboratory 1 Assignment 2. So our group members is Tufa Wafa EL 24001 and Nurul Aisha EL 24049. So Tufa Wafa will present the figure 2 and Nurul Aisha will present the figure 1.
Okay, now we look at theoretical calculation for figure 1, which is its common emitter amplifier circuits. So, first we calculate the RTH using the Thevenin theorem. So, we know that RTH is found by calculating R1 in parallel with R2, which give us 33 kilo ohm in parallel with 3 kilo ohm. So, in this calculation, we get 7.674 kilo ohm. So, next, we calculate ETH, um, which is it's using voltage divider formula. R2 divided by the sum of R1 and R2 and multiplied by VCC. So, ETH we get 2.33 volts. So, in DC analysis circuit, we want to calculating the base current. So, we using Kirchhoff voltage law around the base emitter loop. So, the equation is if ETH plus IB time RTH IE time RE plus VBE equals to 0. So, since the emitter current IE equals beta plus 1 times IB and we assume that beta equals 100, so we substitute in this equation. So, we know that VBE is 0.7. So, we get base current IB equals to 15 mu ampere. Okay, next, the collector current IC equals beta times IB, which is 100 times 15 microampere, giving us 1.515 milliamp 1.5 milliampere. And the emitter current IE equals to beta plus 1 multiplied by IB. So we get 1.515 milliampere. Okay, next, for the base voltage VBE equals to VB minus VE. Since we know that VBE is 0.7 and VE is 1.52. So we search VB. So VB equals to 0.7 plus 1.52 equals to 2.22 volt. Next, using KVL around the collector emitter loop, we know that negative VCC plus IC times RC plus IE times RE plus VCE equals to 0. So, when calculating, we get VCE equals to 4 volt. So, the collector voltage VC equals VCC minus VE, which is 10 volt minus 1.52 volt, giving us approximately 5.2 volt. Okay, last, for AC analysis, we want to calculate voltage gain. So the AC emitter resistance RE equals to 26 millivolt divided by IE, which is 26 millivolt divided by 1.515 milliampere. So we get 17.1617 ohm. So the beta times RE equals to 100 times 17.1617 ohm, and we get 1.716 kilo ohm. Okay, last, the input impedance, that is equals to R1 in parallel with R2 in parallel with beta times RE. So we get 1.4025 kilo ohm. The output impedance Zout equals to RC. So it's same, which is 3 kilo ohm. Okay, and when calculating the voltage gain calculation, AC equals to negative 100 times 15 microampere times 3 kilo ohm divided by 17.16 ohm. So lastly, we get 174.8 for the EV. So that's all. Okay, so now we look at simulation result at figure 1 about common emitter amplifier circuit simulation. Okay, now this circuit is powered by 10 volt DC supply, and it has AC input signal of 25 millivolt peak at 1 kilohertz frequency. So we look at DC biasing analysis first. So starting with the bias circuit on the left side, we have a voltage divider formed by R1, which is 33 kilo ohms, and R2, which is 10 kilo ohm. So these simulations show that the base voltage at point V 2.23 volt is approximately 2.23 volts DC. So the base is also receive a small AC signal of 269 microvolt peak to peak with an RMS value of 93.9 microvolt. So AC components is come from the input signal and pass through the capacitor. Next, we're looking at collector side. At point PR1, we can see that R3, which is 3 kilo ohms, is connected to the 10 volt supply. So the collector DC voltage VDC equals to 2.23 is 2.23 volts. Okay, now we see that collector voltage is actually 1.66 volt DC with a peak to peak AC voltage of 6.52 volts, and the RMS AC voltage is 5.87 volts, and the DC component is 5.37 volts. Okay, next we look at the emitter measure at the PR3. So the DC voltage, we see that DC voltage across the emitter resistor R4, which is 1 kilo ohms, and 1.54 volts. So indirectly, DC emitter current is approximately 1.54 milliampere, calculated by dividing 1.54 volts by 1 kilo ohm. And the AC voltage at the emitter has a peak-to-peak value of 43.5 millivolts and RMS 1.56 volts. So, lastly, the peak current through the emitter is 43.5 microampere, and we know that RMS current is 1.55 milliampere. And last, DC current also 1.56 milliampere. So we look at input signal. We see that V1 is 25 millivolts peak at 1 kilohertz with 0 degree phase. So at PR2, we see that the input has a DC of negative 3.55 microvolts and a peak-to-peak voltage of 50 millivolt and an RMS voltage of 17.7 millivolts. So for output signal, the output signal at prop PR4 at DC voltage is 2.64 volts. A peak-to-peak AC voltage is 6.52 volt and RMS voltage of 2.37 volts, and a DC component of 35.5 millivolts. So to calculate the voltage gain, we compare that the output AC to the input AC voltage. The output peak to peak is 6.52 volt and the input peak to peak at the base is 269 microvolt. Okay. So overall, this simulation that this common emitter amplifier is successfully amplifies the small input signal by the approximately 113 times while inverting its phase. Okay, now we look at result comparison. In error percentage, we use the formula uh, error percentage equals to simulation minus theoretical divided by simulation multiplied by 100%. So first, we look at voltage base, which is VB. Theoretical is 2.22 volts and simulation is 2.23 volts. So when we using that formula in error percentage, we get 0.5, 0.45. And V and VE, we get theoretical 1.52 y 1.52 and simulation we get 1.56 and in error we get 2.56. Okay, so now we look at VC. So theoretical we get 5.52 and simulation we get 5.37, but the error is a negative 2.09. So here we look, we have a it have a big error. Okay, so for IE in milliampere, theoretical we get 1.5150, simulation 1.56. So total is 2.88. Invol, invol, in V in V peak to peak, theoretical 25.074 and simulation 15. So we get peak value which is 48.52. Okay, now V out theoretical 4.5 and simulation 6.52. And error we get big error to 30.98. Okay. Finally, we look at voltage gain, AV. So we calculate uh, 1.174.8252 in theoretical, and simulation we get 113.54. So resulting in a negative error which is negative 34.07%. So however, the simulation gain we calculate from the actual measure input and output voltage at the circuit nodes. So the difference when theoretical calculation using a small signal models. So while practical measurement we get a padding effect. So signal source impedance and anything else will get be error lah. Okay, that's all. Okay, this I will show you the simulation demo at figure 1. So the figure 1 is common emitter amplifier. So we this okay. So we're using BGT NPN 2N3904 transistor. Okay, and then we do the circuits given. So the to calculate the value of voltage and current, we place the current at PR1, 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 and also give using the oscilloscope to measure the output waveform. So to find the DC value, we used to simulate. Okay, first we simulate, and then we analyze a simulation. Okay, and then we take interactive simulation. We go to output, and this show all device parameter at the end of simulation and the audit trail. Okay, so audit trail, and then we run the simulation. We run the simulation, and then it will give value of the DC and AC at the every probe of voltage and current in this simulation. So we determine the value of DC values from VDC. Okay, first we pause first, stop first, and then we at VB. At VB, we see that VDC is 2.25 volts. And then for VC, we look at VDC 9.84 volts. Okay, last for VE. Okay, last for VE and IE. We're taking that VDC for VE is 1.58 volts and IDC is 1.58 milliampere. Okay, so next. Okay, so next we to obtain the input and output waveform, we connecting um out, the output and input to the oscilloscope. So to produce this output, we use again to simulate and then we analyze and then still same interactive simulation and then we run and then we run and then you must to go to the grapher, this grapher, and we'll obtain the waveform from this simulation. Okay, this take a look at this. Okay, we take this. Okay, this at waveform at the upper is V out. Okay, and we see that the below is V in. Alright. Okay. So okay. So if you want to find a AV, we simulate again and then we go to and then we go to the analyze and then we go to AC sweep. When AC sweep, so the output we take at the PR5 and PR4. Okay, so and then we run. So this is two type of the wave graph of our simulation. That's all for me. Thank you. Okay, now this is our improvised amplifier design for figure 1 and its decreased value of RC. Okay, now in original design, RC was 3 kilo ohms, but this new amplifier design, we reduce it to 1 kilo ohm. So this circuit still use 2 and 3904 transistor in commutator emitter configuration with 10V supplies, and we maintain that the voltage divider bias network with R1 at 33 kilo ohm and R2 at 10 kilo ohm. So the R2 remains at 10 kilo ohms and the emitter bypass capacitor C1 is still 15 microfarad. So the input coupling capacitor C3 is 100 microfarads and the output coupling capacitor C2 is 15 microfarad. So we know that the input signal V1 is still 25 millivolts peak at 1 kilohertz frequency. So look at the simulation results for DC operating point change. We we see that it changed in the DC operating point. So the base voltage has increased to 2.25 volts compared to 2.23 volts in original design. So the emitter voltage VE shown at PR2 probe is 1.59 volts, which is higher than the previous 1.54 volts. This means emitter current has increased to 1.59 milliampere and calculated by dividing the emitter voltage by the 1 kilo ohm emitter resistor R4. Okay, now the most dramatic change in collector voltage is at the probe PR3. So we see that collector DC voltage of 8.92 volts compared to the value of around 5.37 volts. So this makes perfect sense because with a smaller collector resistor, there are less voltage drop across RC. So the voltage drop across the new 1 kilo ohm RC is only about 1.59 volts, and at the same time is calculate IE times RE, which is equals to 1.59 milliamperes times 1 kilo ohms. Therefore, the collector voltage is approximately 10 volts minus 1.59 volts, and we get 8.41 volts, which is close to our simulated value of 8.92 volts. Okay, at the input side at PR5 shows that the base is receive an AC signal with a peak-to-peak voltage of 71.2 microvolts, and RMS voltage is 2.25 volts. So the input from the source at V1 shows a peak-to-peak voltage of 15 millivolts and RMS voltage of 17.7 millivolts. Is consistent with our 25 millivolt peak input signal. Okay, now for the output signal, we see that DC voltage of 8.2 volts and is peak to peak AC voltage of 237 millivolts and RMS voltage of 9.84 volts. So the AC peak to peak voltage at the collector is 2.237 millivolts with RMS at 4.4 millivolts. So it's smaller than 6.52 volts peak to peak rather than original design. Okay, now we look at the voltage gain comparison. So taking out the peak to peak voltage and dividing by the input peak to peak voltage of 15 millivolt, we get a voltage gain equals to 4.74. So compared to the original design, this is much lower than our original gain 113.4. So this reduction in gain is exactly what expected when we decrease the collector resistor value. So the voltage gain of a common emitter amplifier equals to negative RC divided by RE, where RE is the small signal emitter resistance. So we reduce RC from 3 kilo ohms to 1 kilo ohms, and we reduce it by a factor of 3. So thus the voltage can also decrease uh, by the same factor. So comparing the original gain was about 113.4, and reducing RC by a factor of 3 give us a gain of around 43. So thought the actual actual measure gain is lower to loading effect and measurement points. Okay, so why would we want to decrease the gain? This modification provides several benefits. First, the higher collector voltage give us much more headroom and from the output signal swing before clipping occurs. Second, the amplifier is now more linear because it's operating further from saturation. So third, with a lower gain, the amplifier is less susceptible to noise and oscillation, and it more stable. Lastly, the power dissipation in the collector resistor is reduced, so indirectly we can improve the efficiency. Okay, so the simulation confirms that our theoretical understanding that collector resistor value directly controls the voltage gain of common emitter amplifier configuration. That's all for me.
So I will continue with figure 2. So in figure 2, I will explain about theoretical calculation, simulation results, simulation demo, and also improvised amplifier design. So next, we will continue to the theoretical calculation for BZT common collector amplifier, which is the figure 2. So firstly, we will do the DC analysis, which is we will do the DC equivalent circuit. So first, we will calculate the RTH, which is the parallel combination of R1 33 kilo ohm and R2 10 kilo ohm. So this will give us an equivalent base resistance of 7.6744 kilo ohms. And then we will calculate the ETH by using the voltage divider rule, and we will find the open circuit voltage at the base. So with the supply of 10 volt, the base voltage VB is approximately 2.3256 volt. And then we will calculate the emitter voltage. So we will assume that the standard silicon drop of 0.7 volt across the base emitter junction, and then we will subtract that from VB to find VE, which is equal to 1.6256 volt. And I will proceed to find the emitter current. So we will apply Ohm's law across the emitter resistor RE, which is 1 kilo ohm, and we will find the emitter current is 1.6256 milliampere. So this value is very crucial because it will determine the internal resistance of the transistor for our next step. Next, we will continue to the AC analysis. So um, to do this, we must determine the dynamic resistance RE of the transistor. So when to calculate RE, we will use the standard formula, which is RE equal to 26 millivolt over IE, and we will substituting our DC current of 1.6256 milliampere. So we will get an internal resistance of 15.99 ohm. So from the second picture, the right picture, we can see that the AC equivalent model, uh, which is the hybrid pi model diagram. So the output is taken directly from the emitter. For the output voltage, it is developed across RE. However, the input voltage V in is shared across both the internal resistance RE and the external resistance capital RE. So voltage divider effect. So by applying the voltage divider rule to the AC signal, we can see that V out equal to RE over capital RE plus small RE times with V in. So with an input of 1 volt, so when we substitute the values of 1 kilo ohm and 15.99 ohm, we will get the output of 0.9843 volt. So we will, from this, we can obtain the voltage gain, which is by dividing V out by V in, and this will give us 0.9843 for voltage gain. So, to summarize, our analysis confirmed that the characteristic behavior of the common collector amplifier, which is the output voltage, follows the input almost exactly, which resulting in a positive gain just slightly less than unity. So, this makes it an excellent buffer stage for electronic signals. Next, we will continue with the simulation results. So, this simulation is conducted was conducted using multisim, and we are using NPN BJT 2N3904 as the transistor. So first we will look at the DC values. So at the voltage prop 1, we can see the VC, which is equal to 10 volt at the VDC, which also equal to the values of VCC, which is 10 volt. Next, we will look at the VB. At the VB, the VDC is equal to 2.25 volt, which is at the prop 3. For VE and IE, we can look at the voltage and current prop prop 2, and we can see that the value of VDC is equal to 1.57 volt, while the value of IDC is equal to 1.57 milliampere. Next, we will continue with the AC analysis. So AC analysis is containing V in and also V out. So we can see the V in value at the voltage prop 5, which is the value of V peak to peak is 998 millivolt. Meanwhile, we can see the value of V out at prop 4, which is value of V peak to peak is 981 millivolt. So the division of V out over V in will, or we will obtain the voltage gain, which is 0.983. Now let us see the comparison of the results between the theoretical calculation and also simulation from multisim. So basically, this step is important to ensure that our mathematical model accurately reflects the real-world circuit behavior. So we will see the first section, which is the DC bias comparison. So let's look at the DC operating point. So our calculated base voltage VB was 2.33 volt, while the simulation showed 2.25 volt, which resulting in a small 3.36 percentage error. So, and then the emitter voltage VE and current IE follow a similar trend with the voltage base with an error of about 3.5%. So basically, these minor discrepancies are expected because they typically arise because simulations use more complex transistor models that account for internal parameters that we simplify during hand calculations, such as the exact VBE drop or finite beta values. Next, for the AC performance, so we will see the AC analysis. So the results we can see is more precise. So with the peak to peak input V in of 1 volt, our theoretical V out was 0.9843 volt. So the simulation produced 0.981 volt, a difference of only 0.33 percentage. And but consequently, our voltage gain AV is nearly identical in both scenarios, which is around 0.98. So this confirms that our RE model for the common collector amplifier is highly accurate for predicting signal swing. So overall, um, The percentage error across all critical parameters stayed well under 4%. So if we know that in engineering terms, any error under 5% between theory and simulation is considered as an excellent match. So now I will show you the simulation, the demonstration of the simulation. So first of all, this is the figure 2, the simulation for figure 2, which is common collector amplifier. So first of all, we are using BJT NPN 2N3904 transistor, and then uh, we do the circuit as the figure given. So we to calculate the value of voltage and also current, where we are putting the voltage and current probe, and also we are using the oscilloscope to measure the output waveform. So now to find the DC value, so we will use the simulation, uh, analysis and simulation, and I'm using interactive simulation. So the output is all the parameters at the end of the audit trail. So and then when we run the simulation, so it will give the value of the DC and AC at the probe, at the voltage and current probe. So we determine the value of DC values from the VDC. As an example, for the VB, we are taking the VDC of 2.25 volt. For VC, we are taking the VDC of 10 volt. And for VE and IE, we are taking VDC 1.57 volt and IDC 1.57 milliampere. Next, to obtain the output and input waveform, we are connecting the output and input uh, to the oscilloscope. So to produce the output, so we still use the simulate, and then still use this interactive simulation. Okay, and then we will run, and then at the grapher we will obtain the simulation, the waveform from the simulation. Okay, so here we can see that the value of V out and V in. The upper one is V out, while the below one is V in. Next, to find the phase analysis and also the AV, we will use simulation, and then we are going to use AC sweep and then decibel. So the output we will take from the um, voltage probe 4 and also voltage probe 5. So this will result in this will show us the two of the two of the graph. That's all for this part. Next is how do we reduce the voltage gain AV from the figure 2, which is the common collector amplifier. So in a BJT common collector amplifier, resistor R1 and R2 will form a voltage divider that will determine the base voltage VB. So the base voltage will controls the emitter voltage and also emitter current, which are key factors influencing the voltage gain of the amplifier. So when the value of R1 is decreased from 33 kilo ohm to 10 kilo ohm, as example that we did in the multisim, and also the value of R2 is increased from 10 kilo ohm to 30 kilo ohm, so the voltage divider will produce a lower base voltage. So this reduction in base voltage will cause the emitter voltage and emitter current to decrease. So as the emitter current decreases, the intrinsic emitter resistance Re will also increases. So since the voltage gain of a common collector amplifier depends on the ratio between the emitter resistance and also the sum of the emitter resistance and Re, so an increase in Re will results in a slight reduction in voltage gain. So although the gain will remain close to unity, so this example that we provide will show how adjusting bias resistor value can cause the control of the voltage gain of a common collector amplifier. So that's all for our presentation. Thank you.